Hi everyone, welcome back to AP Physics BC. We're going to continue our discussion on Newton's laws. We kind of talked about the basics of Newton's laws last time, talked about free body diagram, how you solve these problems, and we kind of went through a small example using the three forces that we talked about that are important and the fundamental forces you have to know. Weight, right? And we talked about normal force, and then we talked about frictional forces. So really, in this lecture, I just want to kind of go through two types of problems that always show up on your exam, and then just to show you guys how we can properly solve these problems. The first type is called incline plane problems, and I know you guys hate these because every student I encounter hate inclined plane problems, but I'll show you that with the proper free body diagram, everything will become so easy. Okay, let's take a look at an inclined plane problem. So they always start off with, hey, your object rests on an inclined plane with angle theta, right? And there's a certain amount of friction, mu, right? Whatever the friction surface between the object is. And they will ask you, one, whether this object is going to stay put or it's going to slide down. And if it does slide down, what is the acceleration? Right. So, interesting. Remember we talked about when we encounter this problem, the free body diagram, right? What do we do first? We label all the forces. What are the forces acting on this object? Well, first force, I always like to start with weight, right? Weight is coming down. It's always there. And it's always pointing straight down. Right? Second force, your normal force. Your normal force is a little bit different. We kind of dealt with that a little bit, right? Your normal force is going to be what? Perpendicular to the surface. So if your surface is at an inclined plane, your normal force is going to be perpendicular to that as well. Right? What else? Well, there's no natural force that's pulling this guy down, but if there is, there's what? There's a frictional force that's pulling the other direction, right? Because most likely your block is slide down. If the block slides up, there's another problem, right? The block's going to slide down, so the frictional force is always going to be opposite of that. So number one, we're taking care of labeling all the forces, done. Right? Number two, you want to define an xy coordinate plane and decompose, right? So xy, what would my xy be? I know if the thing's going to slide, it's going to slide along this line, so it doesn't make any sense to make my xy plane the normal one. Right, the vertical and horizontal. I'm going to call this my x, and this is my y plane. Okay? Now, if some of the forces are not in line with xy, what do? We have to what? Decompose them. What force? So normal force is fine. It's positive y. Friction, fine. It's negative x, as we expected. The force that's not really in line is your weight. Right? What is your weight force? Well, if you think about it, I need to convert this weight force into an xy plane. How do I do that? I can decompose this into weight y and weight x, and this angle turns out to be theta. You can do a little bit of math and to figure out why this angle theta, but trust me, it does. It does come out to be theta. Okay? So once we have that, we no longer need to consider your weight. Okay? In other words, weight x will be weight times cosine sine theta. Weight y will be weight times cosine of theta. Okay? So if you think about it, if I move this weight x here, right? This is really the same problem we solved in the last lecture, except instead of flat plane, we tilted it. But we managed to tilt everything in that direction. Right? We managed to tilt everything in that direction. So it's really straightforward afterwards, because if I need to come up with F net of x, it would just be W of x minus friction, which will be mass times acceleration. Right? F net of y will be what? Normal force minus W of y, which will get you what? 0. Because again, this object will never bob up and down. Right, will never bob up and down. Okay? So in other words, you can find your normal force. If you solve for this, normal force is Wy. In other words, it's mg times cosine theta. That is your normal force. Right? Once you get the normal force, you need to plug it in here because Wx minus friction is mass times A, right, where your force net in the x direction. Your W of x, the x component of your weight, is mg times sine theta, right? Minus friction is mu times normal force. Mu times normal force is what? Mg cosine theta is equal to m and a. Okay? And assuming you know what mu is, so if this object is staying put, how do we know if it's staying put? It's staying put if this guy is bigger than this guy, right? Because if it is, your acceleration will be negative. There's no way you can have a negative acceleration. There's no way, because frictional force is a reactional force, right? It's only applicable to a point of what your force is applied to be, right? So if you pulls it up, there's no way friction force is going to pull it up. It only reacts to the weight. So if this guy, for instance, comes out to be 10 newtons, if your weight is 9, you're not going to have a negative acceleration. That just means what? This weight, the x component of weight, is not big enough to counter this force. So it's going to stay put. Even if it's 10, it's going to stay put. If it's 11, then it's greater than that, then you can have an acceleration downward. That's how it works. Okay? And keep in mind, there are two types of friction. There's the static friction, which means a mu s is when the object is staying put. Once this object starts to move, your mu changes to kinetic friction. Okay? And keep in mind that mu s is always going to be bigger than mu k. That's why it's always harder to move the thing or to get the thing to start moving. And once it starts to move, it's a lot easier. Right? Mu s is always greater than mu k. Okay? So that's a secondary point. The more important point is that this problem becomes very, very straightforward. Right? Did I do anything that's different? No. Right? Very fundamental concepts. One, free body diagram. Right? Decompose all the, define my xy coordinate plane. Decompose all the forces and simply went for x net and x net of y and then solve for whatever I need to solve. That's inclined plane. Okay? Inclined plane is not that difficult. Right? Be consistent, follow the rules of free body diagrams, and you'll be fine. Okay? I'm not going to put numbers in because that's silly. You guys should be able to do that. But keep in mind, no matter what you have, any problems that involve forces always have the free body diagram ready. Okay? Let's take a look at the second type of problem, which is a little bit different. Pulleys. What are pulleys? Pulleys are things that changes direction of forces, but not the magnitude. They only change direction. So really the best example of pulley system is something like this. Mass 1, mass 2. Right? I want to know what's going to happen to the system. Okay? What's going to happen to the system? Whether or not, well, if you can imagine, there are only two scenarios, right? It's going to slide or it's going to stay put. Right? It can't slide that way because that's just creepy. All right? So if you think about it, we're going to do the same way. What are we going to do? We're going to do the free body diagram, except we're going to do free body diagrams because there are two bodies. Right? Let's do the first one. What are the forces acting on this guy? Well, obviously, this is weight 2, which is m2 times g, right? That's it. What else? Well, this guy is getting held up by this cord or the string, right? So it's held up by this force I like to call tension 2 because it's second tension on the second object, right? What about the horizontal object? What does it have? That's it, right? If I have to come up with, you know, let's assume the system's going to move this direction, call this direction positive, it'll be what? Force net of y will be W2 minus T2, which will be mass times A2, right? That's it. Very simple, very straightforward, right? Nothing much, right? It's either going to accelerate down or it's not going to do it at all. What about the first object? The first object is a little bit tricky, right? You have your weight 1, right? You have your normal force, right? Because it's making contact with the surface. This guy's not, right? You're getting pulled in this direction by T1, or the tension on the first block, and then you're what? If there's a tension, there must be friction acting on this guy, right? And then so if you translate this here, if you want to do force net of x, so this is object number 1, this is object number 2, okay? Net of 1, it will be T1 minus F is equal to mass times A1, right? And force net of y will be normal force minus W1 is equal to 0. Again, this thing is never going to move up or down, right? That's just crazy. So if you think about it, if I give you mass 1 and mass 2, there are way too many unknowns in this equation, right? I have what? I really don't know, because this is just used to solve for this. I really have 4 unknowns. If you think about it, I have what? T1 and T2, A1 and A2. Right? These are the 4 unknowns in this problem. Right? How do I resolve that? Well, actually, if you think about it, what is the relation between T1 and T2? What is the tension on every single point on this string used by the pulley? They're all the same, aren't they? They have to be, because if there's one point that's subjected to stronger force, that point will snap, right? And keep in mind, pulley only changes direction of force, right? It changes from this direction to that direction. It doesn't change the magnitude of force, assuming it's a frictionless pulley, which we all do. It's an ideal system, right? So every point has to be the same. So there's no such thing as T1, T2. It's the same T, right? It's the same T. One more. What about the acceleration? They can't have different accelerations. If you think about this, this is your system. You're fixed by a certain string length, right? You can't move one faster than the other. In other words, you can't have an acceleration greater than 1 than the other one. They have to move with the same acceleration, right? They have to do this. Otherwise, what would happen? Otherwise, the string will break, right? And they snap, and you have 2 pieces. Okay? So, in other words, in this case, A1 and A2 are the same, are basically both A. So basically what you do is you substitute this weight 1, which is equal to normal force, get your friction, right? And you basically have 2 equations. One is this guy, and the second one is this guy. And you solve for T, and you solve for A, and then you're done. Okay? So keep in mind, for a pulley system, what you have is what? You have a 2-body, but that doesn't matter. You just have 2 free body diagrams and do exactly the same thing, same analysis for each body diagram. This one's easy. It doesn't even have an x component, right? It's just pure y. It doesn't have an x component. It just has pure y, and when you do that, you're done, right? Apply the same forces. Understand that T is the same throughout this, because pulley doesn't change the magnitude of force. Every single point has to have the same force, right? It only changes direction. And also notice that they're the same acceleration because they're the same movement. Once you do that, you're done. Okay? So 2 of the most popular problems, practice a lot, right? But the principle doesn't change. Free body diagram and solve for force net, and you're good. Okay, so no matter it's inclined plane, which means you just tilt your coordinate system, or it's a pulley system, which means you have 2 free body diagrams. That's it, right? 2 free body diagrams, and you're done. So these problems are not that difficult. If you practice, and then hold on to the fundamentals, you'll be fine.